In this video, we're going to learn about acid and base dissociation constants. First, we'll learn the difference between a strong and weak acid and base. Then we'll learn how to write a dissociation constant expression. And then finally, we'll solve a sample problem in order to use those dissociation expressions. So first, the difference between a strong and weak acid. When an acid or a base, we could also say a base, dissociates or dissolves in water, it's going to split apart. And for acids, they're going to split into hydrogen ions and then some kind of anion, something with a negative charge. And so hydrogen ions have a positive charge. If an acid or a base is going to be strong, it means it's going to dissociate 100% or completely. So for an acid, we would have all of our acid molecules here put into water, and as they dissolve, they would all split apart, and we get all these free ions floating around in the solution. And so that gives us 100% of these acid H plus ions, which makes an acid an acid. For a weak acid or base, only some of those particles are going to split apart. So with our weak acid, maybe only one of these will actually split, whereas all the rest will stay together. And so we don't get as many of these H plus ions as the strong acid. With a base, we're not concerned with H plus, but we're concerned with hydroxide, this ion right here. This is what makes a base a base. And usually we have some kind of metal, this is sodium, that's attached to that hydroxide. And so when it dissolves or dissociates, we're going to end up with the metal ion, which doesn't really do anything as far as making something acidic or basic. And then we have the hydroxide. And so the more hydroxide ions we could get into solution, the stronger the base is going to be. So we can determine how strong or weak an acid or base is by calculating the dissociation constant. Now, the smaller the dissociation constant, the weaker the acid or base is going to be. The dissociation constants are going to be based on the way that these substances are going to split apart or dissolve. So we'll start with this one. This is hydrochloric acid, which is a strong acid. When it breaks apart, we're going to end up with the hydrogen splitting apart from the chlorine. And so we'll get this kind of thing in solution. So the dissociation expression is going to compare the amount of stuff that split apart to the amount of stuff that remained whole. And for an acid, we use the symbol K sub A, and this is the dissociation constant for an acid. And what we do is we take the concentration of the two products, that's these things over here. Generally, it's always going to be H plus and some anion. So we'll take the concentration of the hydrogen ion times the concentration of the anion, and then we divide that by the concentration of the reactant, which is the thing that we started with. So we're comparing how much of the stuff split apart, this stuff over here, to how much remained intact. And so the bigger this number, and the biggest we would get is 1, but the bigger this number, the stronger the acid is going to be. Here's another example below this, and this is called acetic acid. It's a little bit different looking, but it works the same way. We're just going to take off one of these hydrogens. This is a weak acid, so it will not dissociate completely, and we'll end up with the anion here and a hydrogen ion. And to write the dissociation expression, we would take these products and divide by the reactants. And then finally we have a base, and in this base we have a sodium and a hydroxide. They're going to split apart, and we'll end up with the sodium metal and a hydroxide ion. And since we're dealing with a base this time, we're going to use the symbol K sub B. And we'll do the same thing where we take the products, that's going to be the concentration of sodium compared to the concentration of hydroxide, and divide that by the concentration of the thing that we started with. So let's go ahead and try calculating one of these constants. So this problem says a 0.1 molar solution of acetic acid has a hydrogen ion concentration of 1.32 times 10 to the negative 3 molar. And it says, what is the acid dissociation constant? The first thing you want to do when you're solving a problem like this is write out the dissociation chemical reaction. So this is acetic acid. That's the chemical formula for acetic acid. And this is going to dissociate into H plus and the anion just like that. So we'll start with that, and what we want to do is we want to look at the initial concentration of acetic acid, what we started with. That's going to be this amount right here because we started with 0.1 molar solution. And so this represents before this thing is dissociated at all. So this is our initial, that's what I stands for. And these are both going to be 0 because nothing's split apart yet. Next we'll look at the change, how this is going to change, and we'll represent that by SC. And the hydrogen ion concentration is going to change from 0 to 1.32 times 10 to the negative 3. Now based on this chemical reaction, the stoichiometry here, it's a 1 to 1 to 1 ratio. And that's looking at the coefficients in front. If there's nothing there, that just means there's one of those substances. So if this goes up, it's increasing by 1.32 times 10 to the negative 3. This has to go up by the same amount because it's a 1 to 1 ratio. Now since this stuff is splitting apart, the acetic acid is splitting apart to form this, every time one of these splits apart, this is going to go up, which means this has to decrease. So as these go up by 1.32 times 10 to the negative 3, this must decrease by the same amount. Again, it's a 1 to 1 to 1 ratio. So we have these parts going up, I can say plus, and then this part decreasing. Finally, we'll see how does it change or what's the result. We call this the equilibrium. And so this is commonly called an ice chart, the thing that we're creating here. It starts the initial amounts, the change, and then the equilibrium. All we do is we look at each column and we just do the math here. So we'd have 0.1 minus 1.32 times 10 to the negative 3. Then over here we're just adding that amount. Now when we plug in the information into our equilibrium expression, it's the amounts at equilibrium that we're concerned with. So we always have to start with this given information and then decide how much is everything going to change by. The equilibrium expression for this is going to be the concentrations of hydrogen times the concentrations of this anion over the concentration of the original acetic acid. And now I can just plug in all the information from my chart and then solve for the Ka. And I end up with a Ka that's going to be equal to 1.77 times 10 to the negative 5. And so there's my acid dissociation constant for acetic acid. And because it's a really small number, I know that acetic acid is going to be a weak acid and it's not going to dissociate very well. And so that is acid-base dissociation constants.